We're going to be looking at some parts of similar triangles, and we have three theorems on page 501, and we're going to look at a couple of these with associated problems, and we're going to discuss the third. And so this first theorem that we're going to take a look at is, it states that if two triangles are similar, the lengths of the corresponding angles are proportionate to the lengths of the corresponding sides. Now in this first triangle right here, we have an altitude that is running from the vertex down to point D. And what defines it as an altitude is it's running from that vertex, and at this intersection of CB, it's forming right angles. So an altitude is going from the vertex to the base, in this case, at a point where right angles are formed with that base. And we see this same thing here on this segment FJ, where it's forming right angles as it intersects with the segment HG. And so those two altitudes are proportional, and therefore they are proportional. They're also, we're going to see proportionality between corresponding sides. And so let's look at our example here down here at the bottom. Now, if you can visualize, actually, this triangle may be rotating in this direction up here, but we can see it from how it's formed in other places. So here we've got an altitude that is running MP. We know it's an altitude because it's forming that right angle right there. It's going from the vertex M to point P, which is an intersection with KL. And on this smaller triangle, we see an altitude going from YQ, because it's also going from that vertex Y to a point Q, which is intersecting between XZ, let's say, or ZX. Now, the other thing that we see about this is we've got a measurement of a side. I'm going to go back to the left. We got this measurement of this side, and this is an adjacent side to this angle that we've got marked with one little angle mark showing congruency, and that's 20. And it's showing congruency with this angle here at, well, just angle X, or YXQ. And we know the length of that side, which is also adjacent to angle X. So let's set up our proportionality statements. We're going to start here with the proportionality of the altitude, and we just want to do this in the same way. So I'm going to use, let's go 16 over X, then is equal to, and since I started with 16 over here, then we're also going to use this side length KM, 20 over 15. All right, let's do a little bit of cross multiplication. So we got 20x equals 16 times 15. Let's see, 16 times 15 equals 240. And we're going to divide both sides by 20. And so x is going to equal, that's a bad looking 20 right there, isn't it? Let's change that. 240 divided by 20 is 12, I believe. Yep, it is 12. So here, the altitude in this smaller triangle is 12, and we're able to determine that by the lengths of corresponding altitudes are proportional to the lengths of corresponding sides. Now let's go look at another one that involves, I believe, an angle bisector. Yes, it does. All right, so here we got another theorem that says if two triangles are similar, the lengths of the corresponding angle bisectors, the lengths of the bisectors are proportional to the lengths of the sides. So we looked at altitudes. Now we're looking at an angle bisector, and we can identify these as angle bisectors. This segment LP here obviously is an angle bisector because we see congruency with KLP and MLP. And again, segment RT in this larger looking triangle is an angle bisector because we see points of congruency with angle QRT to SRT. Now, that being the case, then the angle bisectors are proportional to corresponding sides. And so let's go look here at our diagram. I'm going to use kind of the one that's on the top left. If I look really close, and this is in your book on page 502, I see that this segment TP is an angle bisector because I've got angle congruency on either side of that bisector. So in other words, angle STP is congruent to angle RTP, and we also see that we've got congruency where segment TP intersects SR, and so I've got congruency here and I got congruency here. So let's look at this second diagram. Again, I see angle bisectors right here where we got an angle UWQ is congruent to VWQ, so that segment WQ or QW is definitely an angle bisector. And so the angle bisector we've got a measurement for, and the side opposite where the angle is being, the two angles are being bisected, we see points of congruency there. So we could then set up our ratio, our proportional ratios in this manner. So our points of our angle bisector is going to give us a congruent proportion. So let's say we got 13.5 over 9. And we want to find x. So these corresponding sides also should be proportional. And so we got 3. All right, so then we got 9x. We can cross multiply. So we got 9x equals 13.5 times 3. 13.5 times 3, that's 40.5. And let's divide both sides by 9. And when we do, let's see, 9 will go into 40 4 times. That'd be 36, 4 left over. And 9 will go into 45. 5 times, don't forget my decimal. And so 4.5, x is going to equal 4.5. So there we've looked at altitudes, we've looked at angle bisectors, and now we're going to just discuss medians. So let me move over to that theorem. All right, so here we've got two triangles, and we've got a median. It's bisecting, in this case, it's bisecting angle C, it's bisecting Y, but we don't see any point of congruency, so it's not an angle bisector. And the point of intersection here at point D and in point Z, we're not forming a right angle, so it's not an altitude, it's not an angle bisector, but we do see congruency and the fact that it is bisecting AB and WX at the midpoint. And this is making it a median, where it's coming from the vertex to the opposite side and we are intersecting at the midpoint of that opposite side. And so again, if that's the case, the medians, CD and YX, are going to be proportional to corresponding sides. And we can use that theorem of similarity to find measures within a triangle. Okay, well, that's pretty interesting stuff, don't you think?